Good morning. Is everything going well so far? Any questions? All right. I don't see any questions. Let me open the transcript. I'm not in the Monday tutorial, but I could see it in Gradescope. I'm not sure. Just post it on Piazza and we can take care of that. All right. So we're gonna do now spanning sets and a little bit of some subspaces, which shows up in the homework too, which we will post um, this week. Right, so this is 1.3. All right. So you start with some subset S, usually it's some countable subset, usually. Make this smaller. Usually it's some countable subset, like V1, Vn, and you have a vector space V, and by linear combination, we mean take all the elements, any subset of this set, and look at linear combinations of them, right? So suppose S is x1 to xm, we take some subset of them and we write a linear combination. Okay, so that's what linear combination means. You take elements from the set and then coefficients from the field. Okay. By span of set, we we are talking about taking all possible linear combinations. Okay. So for example, let's say S is just the element 1, 0. Okay. So this is the vector over here, 1, 0. Then if you take all possible linear combinations, span of S will just be the span of A times 1, 0 for all real numbers A. Okay, So namely the x-axis, because you can go positive A and negative A. So you span the entire line, right? Okay, I think, yeah, I mean, in 2 to 3, you've seen this stuff for sure. If the set is empty, then we just define it to be the 0 vector. So 0 vector. Okay. And yeah, as I mentioned, S is often a discrete set, like a bunch of vectors. So you often have that S is only a strict subset of the span, right? Of course, S could be, so for example, right? S, you can also have S is equal to span S, right? Just take S to be, the span of 8 times 1, 0, the one we just talked about. So in a way, span of span gives you again a span. I mean, anyways, that's sort of a stupid thing, but yeah. Right. Oh, M is what did I write M? Oh no, this is N. Sorry. Yes, thank you. I'll fix that. All right, and if W is equal to the span of S, then we say that span of S general is W. So in our example, take W to be the x-axis. Then this is in the span of 1, 0. All right, so the simplest example is when you work on Rn or Cn, and you just take a collection of vectors, right? And the span is just the linear combination of them, like this set over here. Okay. All right. Yeah, I think this is simple stuff. It's not. Of course, what we're interested in is what exactly is that. So it has a closed form and it's just the this form x comma y comma 0, where x and y are in R, right? So the span of these 3 vectors is just the R2 copy inside R3. Okay. I think I make this comment here that note that the third vector over here is redundant because it can be generated by the first 2. So in other words, this is also the span of just the 2 guys, 1, 0, 0 and 0, 1, 0. So you will see that many times we're given some collection of vectors, some data set, and we only need like a couple of them. We don't need every single data point. We just need enough to span our data to get some pattern. Okay. Is that okay? Yeah. Now in the complex case, remember we had this rotation matrix and we computed its eigenvectors and they were I1 and minus I1. And so this is a vector of the form A plus IB, C plus ID. So this is inside the Cartesian product of complex. So we just say C2. So even there, we can talk about span, but be careful when we talk about span. We have to always have the scalars be from the field. So we're not talking about scalars from real numbers or rationals or whatnot. It will always be from the underlying field. Whatever the vector space is, every vector space has some corresponding field. So we always have some field in mind. We never just mean vector space. We mean vector space with some underlying vector field, with underlying field. In a question when they don't explicitly mention a filter for what should we do, they always do. You will have to show me some example, but it's always yeah, it's always part of it. You can't even write down, like for example, right? Yeah, I mean, I can think of you can't, because you cannot. People will ask you, okay, what do you mean by scalar multiplication? You will have to tell them. They will have to tell you. Oh, I mean when you multiply by this number. So it's always you will have to show me some example where they don't mention it. It will always be because it's mentioned somewhere else in the book. But you just cannot. You always have to mention both. I will have to see. I don't remember. Okay, I mean, I don't have it in front of me. Let me see. So what did the homework 2 say? Okay, let me go find what exactly the problem was, because I don't remember. So problem 2. Right, yeah, it will be, so in problem 2, the vector space is abstract. So the vector field will also be abstract. So the field will also be abstract. Yeah. Is that okay? Oh, it will be some F, arbitrary F. Yeah. Good. All right. Okay, so now let's prove some results. One result is that given any subset from that vector space, if you take its span, then that span will be a subspace. So let me remind you, that means that that is also a vector space. So also a vector space inside V. Okay. So remember by that theorem, I think that I don't remember the numbering. Was it 128 or something? But we had this theorem for closure that it's sufficient. Once you show closure, you get subspace. That was the sufficient criterion When you say span, it means the vectors composing the span, right? Composing. So S are the vectors. These are usually the vectors. So, V1 to Vn, and this is the linear combinations. So you take A1, V1, AN, Vn, AI in V, in the field, and Vi in the set. So you take all possible combinations. Right, so here it suffices to show closure, and that will show subspace. Without loss of generality, we can assume that S is non-empty, because then if it's just empty, then its span is just the zero vector, and you can check that the zero vector has closure, because A0 plus 0V is equal to 0V, which is in the span of the empty set. It's nothing more complicated than that. No, V1 to Vn are not just subspace. V1 to Vn are vectors. So 1, 0 is just an element. So 1, 0 is not a subspace. Combinations of it are. So this is a subspace. This is not a subspace. This is just one element. It just means without loss of generality. Without loss of generality. But I have to justify that I can do this without loss of generality, because if S is empty, then you get it immediately. All right. Right, so let's show closure. So you give me two elements, X and Y, and you also give me, so you give me two elements, X and Y. Since they're in the span, they're linear combinations of the V guys, where M and M could be different. They don't have to be the same, right? And yeah, so then what's the trick? So if one is bigger than the other, then, and you take C to be from the field, you have this grouping, right? Where you group the A's and B's together. And you're left with the extra B coefficients. And what do you note? You note that, well, this guy is in the field, right? Because the field is closed. The field has closure. So each of these summations are in the field. So in a way, you can call this, I don't know, row 1 to row n. So you just get another linear combination of vectors in S. So we're in the span. I think that's okay, right? Is there a reason why span of empty is 0? Well, this is how we define it, like by definition. That was the definition for empty set. We have to define it something. So we define it to just be the 0 vector, which kind of makes sense, because if you don't have any element, you're sort of stuck at the origin. Like you cannot scale. There's nothing to scale. There's nothing to add. Does that make sense? Like, Kellyanne? It's just by definition. So it's not a result. It's definition. Yeah. Why are both X and Y not composed of vectors until Xn not composed of vectors? But they don't have to be, right? Yeah, they don't have to be. So I wanted to do it in a more general case just to get you going. So for example, suppose X is 1, 1, 1, 0. Suppose Y is 1, 1, 1, 1. They, some of their components are 0. Of course, I could have written, you know, I could have written it and then just say that AN or AM is 0. But I just want to practice that they don't always match. Okay. All right. And then same thing. If one is bigger than the other, then you have this formulation. Oh yeah, even for that, n less or equal than m, you can do without loss of generality. Yes. And you can also take n to be m, and then just let some of them to be 0.
Yeah, no, that was my question because
No, yeah, yeah, absolutely. You can take them to be 0. They're elements of the field, so it doesn't
no,
matter.
yeah, I get that.
So
It's
for
just
me,
that
this is more pedagogical. This is not the shortest proof. It's more like just to see what's going on.
I see.
Yeah.
Okay.
Yeah. The shortest proof is just take n to be m and allow an to be 0, like am to be 0. Yeah. So sometimes I will do this. Sometimes I will take like a longer route just so that we see what's going on at the back. Yeah. But yeah, of course, there's a much shorter proof. All right. Yeah, so this is the example for polynomials, and just to see that we don't just work with vectors. Here you have 3 polynomials: the constant polynomial, the linear, and the quadratic. And the linear combination gives you some other polynomials, this guy's over here, right? And right, and this form is always too cumbersome. So the question is, can you make it cleaner? And the answer is yes. And why is that? The answer is yes, and we get P2R. And why is that? Because we can absorb this 1. So we can also write this as the span of B11, B2x, and B3x squared, right? So yeah, anyhow, so which is just P2R. And here B1 is equal to A1 plus A3, if you like, over here. Right, so many times again, you will have some vectors that are not in like standard form, but they still give you the full space. Okay, questions? Right. All right. Yeah, so this is one simple example. Another example done in your book, in one of the exercises, is the following. So you have these 2 subsets that are inside a function of R. So let me remind you, these are all the functions going from R to R. Okay. This. And these are 2 subsets of this vector space. This is a vector space. And let's look at their spans. Oh, okay, yeah. So yeah, let me ask this in the chat. Do you think that these 2 sets have the same span? Like yes, no? What's your guess? And it's some yeses, no, no, yes, yes, yes. No, no, no. Yes. No, no, yes, yes. I see. Good. All right, let's see. So let's check. So we have these two identities, okay? These are called the trig sum identities. And for them to have the same span, you will need to generate one from the other, okay? So let's show first that span of S1 is contained in the span of S2. I think that's the easier one. So how do you do that? So the first guy is easy, right? You already generated it. So you have sine x cos x is equal to a half of sine 2x. So one guy is out. Second guy, sine squared 2x. So from here, now I have to remember my identities. So basically this is, what is it? 1 minus 2 sine square x and also 2 cosine square x minus 1. Where I use the identity 1 is equal to cosine square x plus sine square x. So from here, you can see that, let me go on the, over here. So from here, you can see that cosine of square x is equal to what? 1 plus cosine 2x over, let me do it this way. So 1/2 times 1, and then 1/2 cosine 2x. So here again, we generated cosine of 2x using these two coefficients. And you can do the same for sine square x. There will be some minuses. So 1/2, 1, and then plus minus a half cosine 2x. Okay, so we generated each of the vectors using the vectors of the other set. Is that okay? So that's the main idea. That's how you show one direction, and the other direction, I already have it, right? So I already have that sine of 2x is equal to the linear combination of this, cosine 2x linear combination of these two guys, and the constant vector 1, it's the summation of these two. So this is the easy one. So that gives the reverse span of S2 inside span of S1. So yes. Okay. All right. All right, let's see. So in your homework, you have to deal with modular fields. So I thought I should do an example with them, just to, you know, practice a little bit and get some of your questions if you have any. So here I take the vector tuple, two components, and I take my coefficients from here, from the modulo group. So just to remind you, you have the following things. So 0 plus 0, 0, 1 plus 1 is 2, 2 plus 1 is 0. Yeah, like so modulo arithmetic. 2 times 2 is 4, which is 3 plus 1. So you get 1. Yeah. Okay. So you have modulo operations for F3, and you define a vector out of it. And one reasonable question is, how big is this vector space? Right? And for modulo, it's easy. So you have 2 entries, and you only have 3 choices for each one. Right? So that means, you know, many of you have already formed the tables, so you will have 9 elements, right? So you have 9 possible elements for this vector space. So that's how big the vector space is. It's 9 elements. Okay. Is that okay? All right. All right. So let's take an element from there, the element 1, 2, and let's look at the span of it. So yeah, so let's look at the span of this guy. So what do? What does it mean to look at the span? It means you take all scalar multiples where your scalar comes from the underlying field. And this is the modulo group. So let me do it. So, and you only have 3 choices. So if A is 0, then 0 times 1, 2 is equal to 0, 0. That's easy. What about A equal 2? What's 2 times 1, 2? What do you think? What vector does that give you? 2 times 1, 2. Any guesses? Yeah, 2, 1. So we have 2 times 1, 2 times 2. So you get 2, and then you get modulo arithmetic, you get 1. And for A equal 1, you get the 1, 2. Good. All right. Now, the span for 2 vectors, you have to do the same thing. So I grouped it into 3. That's because of how I did my calculus, my computation. So the first one, I set A to be 0. Okay, I set A to be 0, and then I run through B 0, 1, 2. So this is the same as before. Here I add, I set A to be 1. So I have 1, 0 plus B 1, 2. So I get these 3 elements. And here I set A to be 2. So I have 2 times 1, 0 plus B 1, 2. And these are 9 elements. So this is the entire space. Okay. Is this because scalar multiplication was defined as modulo? I'm confused as to why the entries have modulo. Both scalars and entries are from F3. This is the same thing with reals, right? Similarly to reals. So, you know, if you look at R2, right, you have X, Y, but your scalars are also from reals, from the underlying field. They're all from the reals, same field for everybody. So it's the same idea. You should keep in mind the reals when we do this, because it's the same sort of structure. Okay. So the field is 0, 1, 2. I'm just confused about what the modulo is adding here. Well, like before, right? When we, look, how do we get this vector to 1? We did 2 times 1, 2, which is what? Which is 2 times 4, right? But this is 2 times 3 plus 1. And all the computations here are done modulo. So this is 2, 1. The 3 disappeared, right? Right, yeah, okay, good. So yeah, we got the space. All right, so this is a prelude for homework 2. In homework 2, we will explore some of the properties for this, but I thought I should at least talk about it so that you know what's going on. So we start with 2 subspaces, W1, W2. So they are vector spaces themselves. And their sum is the following set. So you take all the x from the vector space V, and you can write it in the following way as W1 plus W2. So I should do an example right here. So take W1 to be the span of, let me see, 1, 0, 0. And take W2 to be the span of 0, 1, 0. Okay. And then W1 plus W2 will just be, I mean, I have to prove this. I will prove it next. It will just be the span of their sums. I mean, this requires proof. This is not immediate. But yeah, so it will be the sum of the, it will be things like this. Yeah, okay. So, but let me write it formally in the definition. So these are all the x in R3. So that x is equal to A1, 1, 0, 0 plus B, A plus B in 0, 1, 0. And from here, you can show that this is the case. But just the definition is you look at all the elements in your big vector space V, in this case R3, and you require that X can be written as the combination of elements from W1, W2. Okay, so that's the definition of this guy, of this spanning, of this summation. So yeah, this could be W1, this could be W2, and yeah, their sum will be actually the entire space in this picture. Because you can generate any element using their linear combination. So this came up somewhere in Piazza that, so this is not the union, right? So summation is not, it could be different from, could be different. So let me say could be different. So where am I? Yeah, let me say it here. So this could be different. They could be equal, but it could be different. So I think I had an example. Yeah, I will show you an example right away. But again, let me define union of subspaces. So this is the definition. So it says that you take any vector, let's say from Let's do the same example. So span of 1, 0 and W equal to span of 0, 1. It says that their union is an element from either W1 or W2. So in this picture, V is R2, W1 is this, and W2 is this. Oops. And this is W2. And then this union says you either pick it from here or from here. This is what the union is. So this is the union. Whereas their sum, so they're just the X, Y axis. Whereas W1 plus W2 is the entire space R2. So they're not equal. Is that okay? So you understand? Union and summation can be different. Okay. All right. Okay. All right. So yeah, let's do an example. It's the same one I just talked about, but let me, I typed it. So you take S1, S2 to be these two vectors, just the standard basis. So this guy and this guy. And then we want to figure out what is their span, the summation of their spaces. So recall, we just showed that each one is a subspace. And now the claim is that if you sum their spans, you get the span of the union. This is the claim over here. That somehow you can bring in the this additive operation. So this is a proposition in your book, and I want to just catch the idea for this example, because you're gonna do some of it in your homework. Okay, so let's see. So here I'm showing that span of S1 plus span of S2 is inside span of S1 union S2, namely the union of 1, 0, 0, 1. Okay, so let's show that first. What do? Well, you take an element from this sum, V in W1, W2, but by definition, V will equal W1 plus W2. This is the definition for being in this summation. That's all. There's nothing else. But then we know that each one of them is a spanning set. Okay, we know each one of them is a spanning set, so you can write it as A1 times 1, 0, and then A2 times 0, 1. Okay, but this is exactly the same as talking the definition of spanning of two vectors, 1, 0 and 0, 1. Okay, so that's how we get that given any element from the sum, you can write it as a linear combination of the vectors, the basis vectors, you're in fact in the span of their union. Okay. All right. So if we have time, I will do this in more. Let's see, how much more do we have? I see. I do some more examples. I have the function and that's fine. If we have time, I'll come back and do the proof in detail. All right. And then conversely, we want to show that the span of the union is inside the summation of the spans. Okay. So what do? Well, since V is in the span of the union, it means you can write it. It means you can write V as A1 10 plus B1 or A2 01. But then we just said that W1 is a spanning set. So we have that this is W1 and this guy over here is W2, right? Okay, but this is just an element of the sum. And that's all there is to it. So we indeed have, in a more general setting where you have many more vectors, you always have the following state, that summation of spans is the span of the union. This is always true. Okay, not just in this example, but the proof that I did generalizes. I mean, instead of putting 1, 0, you can just put V1 and V2. And it's the same thing, no different. Okay. So let's do some examples just to get you going. So we look at W1 to be P2, and we take W2 to be the span of just the X3 guy, the X3 polynomial. And we want to study their sum. So we just proved the following. So since P2 is the span of 1x squared, we just showed that P2, well, let me do it this way. We just showed that W1 plus W2 is equal to the span of 1x squared x cubed. Is that cool? So from now on, you can just use that. You can use that the summation of them is equal to the span of their union. And I also do it here by example. So yeah, so I take their summation and I show that you can write it as an arbitrary polynomial in P3. Okay. So yeah, we have that their summation is equal to P3. So here you can, as a middle step, you can write what I just said. Okay. All right. So let's do one more example. Take the following two vector spaces. One generated by sine squared, cosine squared, and then one in sine to x. And we want to study their sum, but we just proved that the we can just use that the sum of their spaces is the span of their union. And so let me do the middle step here. So we have W1, W2 is the span of sine squared, cosine squared, 1 sine x, sine to x. And from what we just talked about, you can simplify things. So you can drop these two guys can be replaced by cosine of 2x, because cosine 2x and 1 generate them. I don't know. Anyhow. So yeah, okay. Thank you very much, guys. In this case, is AI in the real or just abstract again? Let me see. Oh, you mean here? Here I just took so AI and oh yeah, here they can be abstract. Yes. Yeah, we can take them to be from a field F. But in my head, I was thinking of reals. But yeah, in this proof, there's nothing wrong. We can just take it to be from the field. Can one be redundant since sine plus cos is 1? That's not true. Or unless you mean something else. But I think you're talking about sine squared plus cosine squared. Yeah. So, right. Yeah. So another choice, like Meima said, is you take sine squared, cosine squared, and sine 2x. That's another choice. Yeah, absolutely. So that's another choice. Thank you. Great. Any other choices you guys think? So Meima said take sine squared, cosine squared, and sine 2x. That's one choice. I wrote the one over here, sine 2x, cosine 2x. Any other way to re-express this? Let's see. If you have an idea, you can let me know. It's more like a calculus question. Thank you. Oh, sine 2x, cosine. Oh, how did you do that? Okay, let me see. So let me see. Sine and cosine. Sine 2x and cosine square x. Okay. So, and then cosine 2x. Oh, I see. You just used the formula cosine 2x is 2 cosine square x minus 1. Yeah, good. Every one of sine square, cosine square, 1 can be redundant. Right. Yeah. Yeah, this I guess only the sine 2x is the one that we cannot drop. This is like a true independent vector. Yeah, the other ones, yeah, exactly. Exactly, this is right. Absolutely. Only sine 2x is the one. Yes. So only sine 2x cannot be dropped. Yeah. Thank you. So if you don't have any questions, I don't see any question. Is there anything? Somebody wants to talk or something?
Can we ask questions about the
Yeah,
homework?
of course. Yeah, go ahead.
I just had a question about problem 1. when we're working with vector spaces for problem one, we can assume that the axiom of distributivity holds, right? When finding out whether the given examples are vector spaces or not.
Yeah, so what distributivity was an axiom.
Right. So if something, for example, does not satisfy distributivity, then that means it's not a vector space, right?
Yeah, because it's an axiom.
All right. Okay. Okay. That was it. Thank you.
Sometimes you guys overthink it, don't you think? Like, is it the isn't it, I don't know, is it stress sometimes? Like sometimes on Piazza I see like some questions, I think, or I don't know, what do you guys think? I mean, maybe it's like because it's new material. What do you think? Hello, are you
I
there?
guess you just don't want to get it wrong.
No, I know, but like, is it like a confidence thing? Like, I'm trying to figure out myself, like, hello?
Yeah, yeah, I'm just thinking.
How do we build confidence so that, because like you will need it, right? Like in tests and stuff, you will need to be able to be like confident in your judgment. I guess one thing I should say is that whenever you feel that, you know, you can always like dispute, you know what I mean? Like if you feel that you were right and the marker was wrong, you can always fight it. You know what I mean? Like, does that
Or
help?
like regrade requests.
Yeah. Like if you feel that, oh, I might get, like, I think I'm right. And you, even after you get it, you still think you're right. You can fight this, and it always happens. Like people make mistakes in the grading. I wish more people fought for their grades, because TAs, they make mistakes. Many of them are undergrads, so it happens. It's very common. Okay.
I see. Okay. Thank you.
Any other question? Okay, guys, I'll see you tomorrow.